about definite integrals. So far we were doing questions, we did a lot of questions where they were indefinite. Of our homework too, just ones where it was just a symbol, add 1 to the exponent and divide by the new. I introduced this just a couple days ago. What happens when there's numbers on those handles there? How do you handle the math involved? Do you remember it's basically the same? Except for one small difference. Yeah, there's some subtraction involved. Once you figure out the answer to this, you plug in the 3, you plug in the 1, and subtract the 2. So you just go about your business as usual, add 1 to the exponent, divide by the new. The 4 would turn into a 4x. What's missing?
C.
The C. And then you put this reminder stripe down, letting you know that you're still not done with the question, because there's still a 3 to use and there's a 1 to use. So plug 3 into all of this. Okay, 3 to the 3rd is 27. Divided by 3 is 9. So we get 9. Plus, what's 4 times 3? 12. So 9 plus 12, 21. 21 plus C. So when you plug that in to this, you get 21 plus C. Then it's the 1's turn. The 1 is called the lower bound. What's the 3 called?
Higher bound.
The upper bound, right? So plug 1 into this, and you get 1/3 plus 4, which is 4 1/3 plus C. And then once you go that far, you just subtract the 2. So use the calculator to help you with some of the arithmetic if you need to. 21 take away 4 1/3 would be 16 2/3, right? C minus C. Nothing. The C's disappear, which is a good thing. Now, we talked about a question like this on Monday, and I actually mentioned just in the title that it involves area. So actually, this is going to represent the area under that equation.
Under a curve.
Y equals x squared plus 4. This is called the Fundamental Theorem of Calculus, and this is how antiderivatives were actually discovered and actually how they were first used. They were used to actually try to figure out the puzzle of how to find the area of a shape that's not a square, not a circle, not a triangle, not a trapezoid, but some shapes that are a little bit more complicated. So let's do that now. So on your paper, let's graph the equation. Graph this equation. Y equals x squared plus 4. Do a really great detailed job of graphing it. So the graph of x squared plus 4 looks like this. The answer to the question was 16.6. So how's the area showing up as 16.6? Well, 16.6 was the answer, but in the question, the symbol looked like this, the integration symbol. And the numbers are really important. The numbers on the question were 1 and 3. Or 1 and 3. What variable did the 1 and 3 stand for, x or y?
Y.
Well, when we plugged them in, we plugged them in for the x. So, and this is the lower bound. X equals 1 is the lower bound. So the lower bound is x equals 1, which is right here, huh? It's x equals 1. What was the upper bound?
3.
3. So here's the upper bound, 3. So in that, between those two red lines right there, if you count up the number of squares in there, and do your best counting partial squares, you should get what for your answer? 16 and 2/3. Let's check it out. There's 1 square, 2, 3, 4, 5, 6, 7, 8. So far really easy. 9, 10, 11, 12. Looks like we got 13 full squares. And then you sort of have to, estimate. So we got 13 squares of area so far. This looks like it almost is a full square. So 13, 14.
15.
This little bit here, and this bit right here makes 15. And then maybe these two parts right here make up about 16. Well, I mean, like I'm saying, I'm estimating around 16. I'm probably a little bit under. And I just need 2/3 more. So this little bit and these little bits right here would finish it off. So the area is believable as 16 and 2/3. Now, looking at it by just graphing it and counting squares, like I just did, it's going to be off. Using the calculus, you can actually get an exact value, which is really what we're after when we're doing calculus. We're after precision. So, I'll show you another one tomorrow that's just a little bit different, but this was a good opening.